Hello there. This video will show you all 4 steps of a hypothesis test using an actual example problem. So in the conceptual lecture, you learned the 4 steps of a hypothesis test conceptually, but now I'm going to break it down for you, practically speaking, as to what you're actually going to be doing when you're testing a hypothesis using data and manual calculations by hand. So step 1 is stating the hypothesis. Or in other words, stating your expectation of what you think your data is going to tell you, and then stating the opposite of that expectation. So your expectation is typically labeled as the alternative hypothesis, or H1, and that's essentially you're going to find a significant effect or significant difference. The null hypothesis, or the little HO there, that is essentially saying there's no significant findings, that your treatment didn't have an effect, or there's no relationship between the variables that you were testing. Now, there's several different types of hypotheses. There's a two-tailed test, which is just stating that you think there's some effect, something's going to happen, right? So for a two-tailed test, you would simply say, I think that my sample mean is going to be different from the population mean because whatever I did in my sample changed them in some way, so they no longer represent the population. So think about an example where we have a a population mean of 5. And let's say that we are thinking that, let's say that we're measuring, I don't know, number of pieces of pizza consumed at a party. And our population mean is 5 among all NSC students. Let's say that's our population. And let's say that we take a sample of those NSC students and we give them an informative pamphlet about how pizza has a lot of calories and it's going to make you gain weight and it's going to give you heart attacks because of all the cholesterol, and we just kind of try to scare you a little bit. So the sample gets this pamphlet, they're a little scared of pizza. We hold another party and we just look at how many pieces of pizza that sample consumes. Well, before we have this party and before we give them this pamphlet, we need to have some sort of expectation as to the effect that the pamphlet will have on the sample. Now, let's say that we're not really sure. Maybe that pamphlet will make them hungry and they may eat more pizza and disregard all the negative information. Or maybe they'll read that pamphlet and they'll be nervous about eating too much pizza because they don't want to risk their health. So if we weren't sure what kind of effect, right, maybe it'll help, maybe it'll hurt, maybe they'll eat more, maybe they'll eat less, we would do a two-tailed hypothesis. And that would look like this in this example with a population mean of 5. So we would expect that the population mean implied by our sample is not equal to 5. It may be higher, it may be significantly lower, we aren't sure. Then the null would be that it would still be equivalent to 5. Now the reason that I don't put a M here, my SAT attempt at a mu is here. This represents the population mean implied by the sample. Remember, we don't care about the sample in of itself. We care about what that sample tells us about the population. So in this silly example, we are testing the effectiveness of this pamphlet on the sample to see if maybe we could give this pamphlet to all people in our population and it would have the same effect. So, of course, let's say we got a sample mean of 4 pieces of pizza eaten after the pamphlet at the following party. Well, we can already see this is not the same as 5, but that doesn't mean that we're going to support our hypothesis. The bigger question is whether or not this 4 is so much different from 5, in fact, more different than the difference we would expect to see just due to chance, just due to sampling error. So is this 1 pizza slice difference way more than we would expect just due to chance? If it is, then we can start to be confident that that pamphlet had a significant effect and we could reject this null hypothesis in support of the alternative hypothesis. So just keep that in mind. This is a mu, not an M, because we are using that sample to represent a population. Just because your sample mean is different from your population mean doesn't mean it's a significant difference. You have to compare the actual difference to the standard error in the denominator, or compare the actual difference to the difference you would expect to see just randomly, just due to chance, even if our independent variable had no effect on our dependent variable. Okay, so that would be what our hypothesis looks like if we were doing a two-tailed test. And our critical value in step 2, the outcome that would support the hypothesis. We're essentially stating, in this case, the minimum value of the z-score required to say that, yeah, our observed difference between our sample and population is much larger than the difference we would expect to see just due to chance. We're confident that the pamphlet had an effect. So in a two-tailed test situation, the reason it's called a two-tailed test, here's our frequency, here's our x and z values down here, we can have an outcome that either falls in the extreme high end or the extreme low end. And we're calling that a significant finding. Now, step 2 is all about finding a critical value, or in this case, a z-score, z-crit, that represents the minimum cutoffs for whatever you calculate based on your actual sample in step 3. Now, we'll do an example with data in a little bit, find those values. For now, I just want to give you a synopsis of the conceptual lecture and how it pertains to what you'll be doing by hand. Now, let's say that we have a specific prediction. We think that this pamphlet is going to decrease pizza consumption. Well, then the way that we state our hypothesis in step 1 is going to be different. So now, instead of just saying equals and not equals to, we think that our population mean implied by our sample is going to be less than the original population mean who didn't receive the pamphlet. And then our null hypothesis just goes for everything else, right? So we are essentially expecting in step 2 that to support our hypothesis, we need to find a z-score for our sample that's out in the high end. Oh, nope. Low end, right? Less pizza. All right, let's fix that. Shoop, down here, low end. We think our sample mean is going to be significantly less than our population mean of 5. So the null is basically covering all of this territory here. Either it's a higher sample mean, they ate more pizza, or it's not really any different from the original. Had no effect at all. So keep that in mind. Usually when I have a one-tailed test, when I have a specific prediction, I'll state my alternative first and then just put everything else in the null. Now let's say that we thought the pamphlet was actually going to make them eat more pizza. So our expectation is that they'd be hungrier, they'd eat more pizza. Well, then we would have an alternative hypothesis stating that the population mean implied by our sample would be greater than 5. So when we draw out our critical region in step 2, remember our population mean's in the middle, we are expecting our sample mean to be somewhere out here in the extreme high end. And under the null hypothesis, all this down here, either they ate less pizza or there wasn't really a change at all. Okay, so that's really covering step 1 and step 2. Then step 3 is just calculating the z-score based on your sample mean, the population mean, and the standard error. Remember, don't use the standard deviation in the denominator. We aren't working with scores anymore. We're working with sample means. So you need to use the standard error in the denominator, which is the standard deviation divided by the square root of the sample size. And what this value tells you is the difference between the sample mean and population mean expected just due to chance, just random differences, or just due to sampling error. So the difference expected between your sample mean and your population mean just due to random chance or sampling error. Or in other words, not due to your independent variable, right? Just random differences. We're going to expect differences no matter what. Now, step 4 of the hypothesis test really requires you to compare what you calculated here to this critical region that you found your minimum requirement for z to call something significant. Now, if you have a situation where your z-score does fall in your critical region, then you can reject that null hypothesis. Hooray! We reject the null, right? We want to reject the null. That's going against what we thought was happening. And you would conclude that, yeah, this pamphlet had a significant, in this case, increase on pizza consumption, if that was the original hypothesis. Now, if you have a situation where you calculate your z-score and it does not fall in your critical region, you have a situation where your prediction does not match the actual data, and so you would have something that falls outside the critical region, and you would fail to reject the null hypothesis, you would have a little sad face and say, my data is not sufficient to conclude that what I thought was going to happen actually happened. So for all of these examples, you need to keep in mind, by reading the scenario, am I working with a one-tailed test? If so, am I expecting a higher sample mean or a lower sample mean? Or am I doing a two-tailed test where any difference on either end of the distribution is fair game? All right, now let's do an example problem using all 4 steps of hypothesis testing to test the hypothesis as to whether or not consuming 6-ounce glass of wine will have a significant effect on reaction time using a standardized driving simulation task. So there's some important bits of information that you need to glean from this story problem. I know a lot of times students look at a story problem and are overwhelmed, but if you break it down into the chunks of information that you really need, it'll make life a lot easier. So the first thing I see is a population mean. That's important. I also see a population standard deviation, a sample mean, and a sample size. So just from the explanation of the study, which you can take the time to read on your own, I know that I'm comparing my sample mean of 422 to the population mean of 400. I know that within my sample there was 25 participants, and I also know that the relative spread of reaction times in the population, or the standard deviation, was 40 milliseconds. Also, I know that my alpha level is 0.01, so I'm only willing to accept a 1% chance of type 1 error, or a 1% chance of saying that my finding is significant when it's actually not, and the difference is due to sampling error and not really due to the alcohol. This is also saying that my sample mean has to fall in the extreme 1% of the sampling distribution. Or in other words, there needs to be a 1% chance of, or less, of randomly getting this sample mean from the population if the sample actually still represents the population and the alcohol had no effect. So the next question I need to think about, because I'm getting ready to do step 1, which is stating my hypothesis, is this a one or a two-tailed test? I know that this is a two-tailed test because I am just looking for a significant effect. I'm not making any specific prediction as to whether or not the alcohol is going to increase or decrease reaction time. I just think there's going to be some sort of difference. Just looking for a significant effect. So when it comes to stating my hypothesis, I'm going to do it in a two-tailed way. So for the alternative hypothesis, what I actually think is going to happen, in other words, I think alcohol is going to have a significant effect on reaction time, I'll state it as the population mean implied by my sample. So if everybody drank a 6-ounce glass of wine, I don't think that their mean would be equal to the original population mean of 400, because the alcohol has an effect on reaction time. So I don't think that the population mean implied by my sample is going to equal 400 milliseconds. Now, if that is not the case, and the alcohol really doesn't have an effect, then the population mean implied by my sample would still be the original 400 milliseconds. Or in other words, my sample still represents the population, the alcohol had no effect. So step 2, this is all about finding the critical region, or the minimum cutoff for your test statistic necessary to conclude that, yeah, there was a significant effect. And because this is a two-tailed test, when I sketch this out, and just a rough sketch of the normal distribution with my, that's a 400, not a 500, with my population mean right there in the middle. Remember, this represents the sampling distribution, or every single possible sample mean from 25 people coming from this population. And the mean of that sampling distribution is equal to the population mean of 400. So that's why I put that in the middle. Two-tailed test, so an effect could be a decrease on reaction time or an increase on reaction time. Now I need to figure out what z-score is right here and right here. Keeping in mind that I'm going to have a single z-score that comes from the table. The negative version of that z-score will go here, and the positive version of that z-score will go right here. So our alpha level is 0.01. And because it's a two-tailed test, I need to split that extreme 1% into two tails, and we're left with 0.005. So we're going to look for p equals 0.005 in the tail, and that's going to lead us to a z-score. That's our minimum cutoff for the z-score for our sample. So let's go ahead and take a look at the table here. So again, we're looking for 0.005 in the tail. Keep on going, getting closer, closer. Oh, here we go. Now check it out. This is 0.0051 in the tail. This is 0.0049. This is the value just above. This is the value just below. And they're both 0.0001 point away from that 0.005 that we're looking for. Because these are both the same distance from the value we need, we are going to go with the larger z-score. So it's a toss-up between 2.57 and 2.58. We are going to select 2.58. It's always best to err on the side of caution and reduce your chance of type 1 error. So 2.58. And because this is a two-tailed test, our z-crit is not just 2.58, it's positive or negative 2.58. And I'm just going to draw this into here. Now when it comes to calculating your z-score in step 3, we're going to be using the z formula, which is the sample mean minus the population mean divided by the standard error. Now I know the numerator is going to be, so I know my sample mean is 422. I know my population mean is 400. Keep in mind that you're not always going to be given the sample mean. You need to remember how to calculate that with raw data, so don't forget that piece. But in this case, the sample mean is given to you. Now, I don't know the denominator. Remember, we aren't going to just plug in the standard deviation because that's the spread of scores in the population. We need to know the spread of sample means in the sampling distribution, or how much error we think there will be between any given sample mean and the population just due to chance, even if drinking wine had no effect on reaction time. So we need another calculation. So I'll put that right here. So our standard error is the standard deviation divided by the square root of the sample size. In this case, our population standard deviation is 40, and our sample size is 25. So this becomes 40 divided by 5, and 40 divided by 5 is 8. So my denominator here is 8. Then we have 422 minus 400, 22, divided by 8. I can't do that one in my head. Let's see, calculator. 22 divided by 8, and we get 2.75. So just to break these numbers down for you conceptually. So this 8 tells me that just randomly, just due to chance, right? Even if drinking wine has absolutely no impact on your reaction time, we would expect our sample mean to be about 8 milliseconds away from our population mean, regardless, right? Just due to chance. That's what this 8 represents, our standard error. Now what we do with our z-statistic is we take the actual difference, right? The difference between our sample mean and our population mean, this 22, and we see how large is that magnitude compared to the difference we would expect to see just due to chance. So what this value for z tells us is that the actual difference between the sample mean and the population mean, or in other words, the actual difference in the sample's reaction time compared to the population's reaction time, is 2.75 milliseconds larger than the difference we would expect to see just randomly, just due to chance. So now for step 4, we need to state our conclusion, or make our decision and state our conclusion. So for making our decision, we need to either reject the null or fail to reject the null. And then that decision is going to inform our conclusion. So in this case, any value in these critical regions, right? Any value for z that's greater than 2.58 or less than negative 2.58 will reject the null. Rejecting the null. Any value that doesn't exceed 2.58 would result in failing to reject the null. Those are the only two decisions that you can have in a hypothesis test. You either reject the null or fail to reject the null. If you reject the null, then you're supporting this. If you fail to reject the null, then you are not supporting your initial conclusion and you have evidence to suggest that you were incorrect with your assumptions. So for step 4, this 2.75 is right about here-ish. It is in the region of rejection. So my decision is to reject the null hypothesis. And then my conclusion, you can really use the original research question to help with your conclusion. So my conclusion would just be that alcohol has a significant effect on reaction time. Now be careful with your conclusions. We can see through this that, yeah, our mean for our sample was actually higher. So reaction time increased with alcohol. But because our original hypothesis was two-tailed in nature, we need to stick to that with our conclusion. So our conclusion would be, I'll just rewrite it, alcohol has a significant effect on reaction time. So based on this study, that's what we can conclude. Now, when you do your step 4, you need to include the decision, either reject or fail to reject the null, and your conclusion needs to include the independent variable, alcohol in this case, the dependent variable, reaction time, in this case, the word significant, and some indicator whether or not it's a two-tailed or one-tailed test. I know it's a two-tailed test, I'm just talking about a significant effect. Now let's say that we got a test statistic in step 3 that did not fall in the critical region. Let's say we calculated this and it was a 2, right? So this would say, fail to reject the null, alcohol does not have a significant effect on reaction time. Now let's do another example. So, same scenario, but this time our hypothesis is a little bit different. So now we're willing to accept a 5% chance of type 1 error, and check this out. We're being more specific, right? So go ahead and try this on your own. Be sure to pause the video, give this a shot, and then resume the video and see how well you did. Okay, step 1. Stating the hypothesis. Well, looking at this, we're being more specific, right? We think the alcohol will increase reaction time. It'll make them slower to react. So our hypothesis needs to reflect that. So for our alternative hypothesis, we're going to say the population mean implied by our sample, if everybody was given this 6-ounce glass of wine, is going to be greater than the original population mean of 400. And so the null is just saying everything else, right? So if it's not greater than, it's what? Less than or equal to, right? So maybe drinking decreased reaction time, or maybe it's really no different. So that informs what the picture of our critical region looks like in step 2. So if we sketch this out, putting our population mean, which is equal to the mean of the sampling distribution in the middle, now we only have a one-tailed test, and we're only looking at the high end here. Increased reaction time, right? So with our alpha level of 0.05, all being in one tail, we can look for p equals 0.05 in the tail, in the unit normal table, and that's going to lead us to a z-score. And the z-score in this case is just going to be the positive z-score, because we're only looking at the high end of the distribution. If we were expecting that alcohol would actually improve reaction time, or make it faster, then we would have this situation, and we'd be looking down here. But that is not the case, right? We're looking for a specific prediction that reaction time will in fact increase. Let's fix this. Okay, so let's go ahead and look at the unit normal table, and let's look for p equals 0.05 in the tail. All right. Oh, wow. We need to go up. Oh, okay. So now we have a situation where we have a value that's just above, a value that's just below, and they're both the same exact distance, right? They're both 0.0005 away from 0.05. So we need to go with the larger z-score, which is 1.65. And it's a positive 1.65 because we're only looking at the high end of the distribution. So remember, the z-score for the mean is 0, and 1.65 is here. Now, just to be creative, just to really help you understand the link between the critical value and sample means, right? Because this is the minimum z-score we have to get for the sample to conclude that, yeah, our sample mean is significantly higher than our population mean. Well, you can convert this z-score back into a sample mean to see not what is the minimum z-score, but what is the minimum sample mean that we would have to get to conclude significance. So and this is just above and beyond, just conceptual for you to understand. You don't have to do this on your own. I just want to help you understand the connection here. So you could calculate your sample mean by taking z times the standard error plus the population mean. So this is the z-score we're working with, so 1.65 times the standard error, which we actually already found over here, right? It's 8. We're still using the same standard deviation for the population and the same sample size, so our standard error will not change. So 8 plus the population mean of 400. All right, so let's plug that into our calculator here. 1.65 times 8 gives you 13.2 plus 400 for 13.2. So just showing you that this critical value is tied to a sample mean. And because our alpha level is 0.05, this is saying that we have a 5% chance of randomly obtaining a sample mean that's 413.2 or greater just due to random chance, right? Even if wine has no impact on driving reaction time, there's still a 5% chance that we could get a sample mean that exceeds 413.2. But we're willing to take that chance because it's a minimal chance. And without even doing step 3, which I'm going to do anyways because that's part of the process, I already know I have significant findings, right? Because my 422 is like here-ish, right? But let's go ahead and calculate the z-score to just confirm this. So for my z-score, and actually we already did this, right? We have the mean for the sample minus mean for the population divided by the standard error. And once again, just like the last one, we have 422 minus 400 divided by 8. So I'm just going to go back and steal that z-score of 2.75. And in fact, 2.75 is roughly here, right? And then we've got, what was it, 422. So no matter what way you look at it, we can see that our sample mean does fall in the region of rejection, in the critical region. The z-score for our sample mean exceeds the minimum value needed to reject the null hypothesis, and the sample mean implied by our critical value for z is less than our actual sample mean. All right, so for step 4, we get to reject the null hypothesis. Hooray! Reject the null. Whoop. You could also say it this way, reject HO, the symbol. And then now our conclusion is going to be a little bit different. Whereas before, we just said alcohol has a significant effect on reaction time because we were doing a two-tailed test. Now we want to say alcohol significantly increased or slowed reaction time. So, alcohol. Again, you want to have the independent variable, the dependent variable, the word significant, and some indication as to whether or not it was a one- or two-tailed test. So alcohol significantly increased, that tells me I did a one-tailed test, reaction time. Done. Now let's go ahead and figure out the so what part of this, right? The practical significance. We know it's statistically significant, but Cohens D will tell us the effect size. So the formula for Cohens D is simply the sample mean minus the population mean divided by the population standard deviation. So with Cohens D, that gives us a nice measure that we can compare to an evaluation of effect size to determine if this effect is small, medium, or large. So for Cohens D, if you have a value for Cohens D that's around 0.20, we call this a small effect. If you have a value for Cohens D that's around 0.50, we'll call this a medium effect. And once you have a Cohens D around 0.80 or larger, you would call this a large effect. So how large is the effect of alcohol in reaction time? Well, our sample mean is 422, our population mean is 400, our population standard deviation is 40. 22 divided by 40, I don't know, let's find out. 22 divided by 40, 0.55. And if you had to evaluate the size of the effect, I would say that this is a medium effect. Alcohol increased reaction time by 0.55 standard deviations. All right, guys, I hope that you feel comfortable using the 4 steps of a hypothesis test to do some hypothesis testing to find out if your results are significant. Keep in mind that for the rest of the semester, you're going to be using these 4 steps. So the more you practice, the better off you'll be.